All right, let's start. Do you have any questions before we start? All right, so we were discussing, oops. So we were discussing, I believe, chapter 13 in the book, test of significance. And so the big context is like this. I guess we have, for one sample, okay, for one sample example, we have 3 types of tests. By types, I mean, they're just kind of one-sided or two-sided. So keep in mind that theta is the unknown parameter. Then we have the following, right? This is two-sided. Let's call it test 1. One-sided upper. Let's call it 2. And one-sided lower. Let's call it 3. Okay. And if you have 2 samples, we also have 3 types. And here we have theta 1, theta 2 are as unknown parameters. So kind of try to distinguish. I don't know what notation I should use, but theta 0 here is some kind of given value, where theta 1, theta 2 here are the unknown parameters, all right? Because you have 2 samples here. One of them, I mean, I guess maybe I can use theta x, theta y, maybe for two different populations, right? So the null is these are equal, and the alternative is, right, they're not equal. Let's call this 4 equal. I guess one bigger. Let's call this 5. And then the last one, let's call this 6. Okay. So I hope you see that these are exactly, exact parallel to the confidence intervals, right? And so their treatment, or the way the stats that we use to construct or to do hypothesis tests here are exactly similar to the confidence interval context. All right. So let me just say that, so these are our setups. All right. These are our setups. So of course, these are hypothesis tests. So the goal, right, the overarching goal is still to construct, right, to construct rejection regions, right? Rejection region C, okay? So the big picture is like this, the big picture. So note that, first note that the hypothesis, the null hypotheses are simple, okay? I mean, including here, actually, all right? So here it's clear that the null hypothesis is simple, right? The null hypothesis is simple. While here, it may not seem like that the null hypothesis is simple because you did not really nail down what the values of theta x and theta y is, right? You just say that these 2 parameters of these 2 populations are equal. But we'll see why they're simple, okay? Because remember that, so basically, maybe this is step 2, okay? Step 2. Observation 1 is like this, maybe. Let me just do step 1. Whoops. So step 1 is we will construct C using test step. All right. So I guess in opposed to instead of likelihood ratio, instead of GLR. Okay. So there are several things to be said about this. First of all, there is an equivalence we can derive. We can derive the test stat from the GLR, but this is not shown in the text. And I'm not sure if we have time to show you this in the lecture. So I'll probably post the slides or something that show this connection. All right. But the point is that here we just go directly to a test stat and we kind of bypass the whole GLR business. Okay. So the test stat, most of the time, I would say probably all of the time even, is exactly the pivot stat. I guess here is R, right? The test stats in the confidence interval construction. Okay. So why actually, why do we approach the confidence interval? Sorry, why do we approach the rejection region construction this way? So the motivation, right? The motivation is because H0 is simple in this setup. So what that means is that the distribution of the test stat is precisely determined, is exactly determined, is completely determined. Under the norm. And that is actually probably the motivation for going directly to the test stat to construct the rejection region in this kind of hypothesis test that we're going to consider. Okay, but so basically what I'm saying is this, that, for example, right, let's look at an example right now. And the prime example we use is we look at x1 up to xn, IID, normal mu sigma square, both unknown. And our null is mu equals to mu naught. Our alternative is mu not equal to mu naught. All right, for example. So this is test type 1, right? So number 1, construct rejection region using the test stat that is exactly the same as the pivot stats in a confidence interval. What do I mean by that? If this is a question on constructing the confidence interval for mu, right, then your pivot stat, remember, would be x bar minus mu divided by s over root n, right? That was the pivot stat that we used in constructing confidence intervals in this setup. So what is the test stat then, right? What's our test stat? Our test stat would be exactly this, except that instead of mu, we use mu naught, right? So our test stat is x bar minus mu naught divided by S over root n. That's what I mean by item 1. Okay. Why the motivation? Why do we use that? Because the null is simple. So I know exactly what this is, what the distribution of this is under the null, right? So in other words, if I call this, right, T of X, then the distribution, right, of T of X under the null is T distribution with n minus 1 degrees of freedom. Sorry, X in here, right? T distribution with n minus 1 degrees of freedom. Okay, so that is exactly the point of point 2. Now, why, right? Knowing the distribution of the test that is kind of important, because that's exactly the ingredient, right, for us to decide alpha, right, or actually to decide the rejection region of size alpha. So this factor, right, this is important. This will help us to construct C, right, of size alpha. Okay, because basically, your rejection region will be something involving this, right, in some region. And so if you know that this has a T distribution, then computing probability of, C under the null, which is exactly the probability of this test stat, which I mean, right, let's just even write that down as X bar minus mu naught divided by S over root n in some region given the null, would just be the probability of the T, right, random variable in some region. And that can be calculated. Okay, so that is the point. But that's not the end of the story yet, okay? Because basically so far we only exploit the structure of the null, meaning it's a simple hypothesis which leads us to a T distribution. We did not say anything about the alternative, right? So that goes to item 3. Item 3 says that, right? So now the region, right? The region, right, of T of X, okay, will be, I guess, influence or will be chosen based on H1, okay? So that it has the smallest beta possible. All right. So basically, once you nail down the test stat, all right, that it's like this, because you know that under the null, this has a T distribution. This region here is still unclear. Actually, there's still many choices for this. All right. Then the fact that the alternative is this is a two-sided test will tell you what region to choose here that will make, right, C the most powerful among, right, the possibilities that you can choose. So it all ends up being very natural in a way. It will end up being, kind of the region that we always go with. But these items 1, 2, and 3 are really the motivations behind, right, the reason why we do what we do. So actually, let's go back to the example and we'll talk about item 4, which is the p-value. So, again, right, using the same example here. Actually, let me say this, right? So let's compare this with, compare the above with the type 2 test, which is H0 mu equals to mu naught, H1 mu bigger than mu naught, okay? So you see that both of these test, right? Both would use the test that is x bar minus mu naught divided by s over root n. Okay. Why? Because they're both test on the mean, right? And they both have the simple hypothesis like this. Okay. And I guess let's not even neglect, right, the fact that we are in the normal population. Okay. So then, but then, right, that doesn't mean that they have the same rejection region. I claim that, right, for test type 1, the rejection region would be, and then you've seen this before, x bar minus mu naught divided by s over root n is bigger than Tn minus 1 alpha over 2. For the test 2, the rejection region would be x bar minus mu naught divided by s over root n bigger than Tn minus 1 alpha. All right. So these are the appropriate rejection regions for each of the tests here, right? For test 1, which is mu equals to mu naught equal to mu naught. Okay. So far, these are my proposals. Okay. I'll discuss this a little bit. Any questions so far? So, right, I mean, again, I hope that these are very intuitive and you would probably not even question me doing this. But let's just look at several things, right? Several things to check. Because these are, you know, these still worth, there's certain things that we should still investigate into these things. First of all, do you see that C1 and C2 has size alpha? If I were to ask you to prove this, would this be easy? I hope. That will be very quick for you to check, I hope. All right, so C1 and C2 are legit in terms of their size. All right. What's a little bit harder to kind of see here is C1 probably is the best for this test, and C2 is probably the best for this test. Best meaning most kind of appropriate, you know, for this structure, right? And by structure I mean the alternative. And that, of course, right, you know, when you want to say best, I always say that it's kind of hard to really nail down what we mean, because, right, provisionally you have to compare with everything. For now, right, let's just compare them among each other. In other words, right, what if I use C1 for test 2? You understand? So in other words, I say that C1 is the rejection region for 1, C2 is the rejection region for 2. But no one, right, says that I cannot use C1 for test 2. And vice versa, right? I can use C2 for test 1. What's the consequence? Why can't I say that in this test 2, I reject if this happened? Right. Yes, right. The beta gets larger. So, but is that clear that the beta, right? So correct, right? So if I use C1 for test 2, then the basically, right? So claim that the probability, right, of C1, right, under the null, sorry, under the alternative of type 2, right, of the test 2 would be, sorry, probability of C1 complement, right, or like this, right? So this is the power. So the power of C1 in the type 1 test, sorry, C2, right? Let's say this, C2. The power of C2 in test 2, which is the most appropriate one, would be higher. So like this. All right. So in other words, that if the alternative is true, right, in test 2, in this test, in other words, if the true mu is bigger than mu naught, then, right, the second region will detect it more often than the C1. That's what we're saying here, right? So here's power larger. If you want to go with power, like what Jianlin was suggesting, you just do the opposite. But this is exactly the point of why C2 is the most appropriate, okay? But when you think about it, this is not quite easy to show. Why? Because the alternative are composite, right? The alternative is composite, okay? The alternative is composite. So this probability we cannot nail down precisely. So for this, you kind of have to show that for each of the theta, right? So for each of the mu in the alternative here, this is true, okay? Something like that. So that is a hard thing to show. But that kind of got swept under the rug by kind of, just saying that this is the most appropriate. And again, we feel, right, that this is the most appropriate. Why? Because, this is a two-sided test, all right? So we reject, right? So X bar is the estimator for mu, okay? We reject if X bar is sufficiently different from mu naught, whether it's sufficiently larger or sufficiently smaller, and that's why we have the absolute value, right? In test 2, we only get that mu is bigger than mu naught. So therefore, right, we reject if X bar is sufficiently bigger than mu naught in the positive direction. We do not reject if it's sufficiently, right, different from mu naught in the negative direction, for example, okay? But again, right, underlying this choice is the influence of H1, okay? So I just want to point that out. And again, if you have time, you can try to think about how to show that. So point 4 would be like this, p-value, okay? So p-value would be something like this. P-value would be, right, the smallest alpha level at which we can reject the null given the experiment. Okay. So here's this, right? Basically, you understand that the p-value would be is reported, right? Would be reported to the audience by the experimenter. Okay. And so the experimenter, after they conduct the sample, right, will report the smallest level at which, right, it's the smallest alpha level at which we can reject the null. So the audience, right, you can see that if the audience, so the logical consequence like this, if the audience choose, right, the tolerance above alpha, right, above p, right, then they can reject. Agree? Because if the tolerance is above P, because P is the smallest alpha at which you can reject, then they can reject the no. On the other hand, right, if the audience choose the tolerance below the P, then they cannot reject. Right, because P is the lowest. Okay, so this exactly explains that rule of thumb where you see when you see the report in R or wherever you see the output, that if P is less than alpha, you reject. P is bigger than alpha, you accept. Okay, but you see, this is the tolerance. This is your tolerance. Okay, and that's the meaning. But of course, the question is, right here, right? P-value is reported by the experimenter. Well, in this class, you play the role of the experimenter. So how do you report this p-value to your audience? Okay. So and so just like rejection region and all these things, there are not a well-defined. There's no like one single way for you to define p-value. One rough idea is that P is a probability that we observe more extreme values than the t-stat, than the test stat, given the no. Okay, and more extreme here, this one is kind of defined by the alternative. Okay. So for example, in test one, right? This is your test stat. This is your test stat, right? In both tests. In test one, more extreme means this, you can observe more test stat bigger than this, or smaller than the negative value of this. Sorry, in the absolute value, right? So in test one, okay, because the no is that mu equals to mu naught, and the alternative is mu is not equal to mu naught. P-value would be the probability that you observe more extreme value in both directions. All right, then there's test stat. So this is your test stat, and more extreme exactly means bigger than the absolute value. Okay, and under the no is already built in when I choose, when I use the T(n-1) distribution. In test two, right, because the direction is mu is bigger than mu naught, the p-value will be probability that T(n-1) just bigger than this. Like that. Is this okay? Any question on this? All right, so then we're just going to go through different tests, okay, different parameters and play with it. Let me just say one last thing. We're going to look at the coding example, and then we're just going to go through all the cases real quick. What I'm going to say is this, that the decision all right, great question. Reached by p-value should be the same as the decision reached by rejection region. Okay, so of course, if alpha are the same, because do remember the difference between the p-value approach and the rejection region approach is that in the rejection region, the experimenter picked the alpha and then report if they reject or accept the null. In the p-value approach, right, the experimenter reports the p-value and the audience, right, choose the alpha to accept or reject. But if the alpha chosen are the same, the audience, right, and the experimenter should reach the same conclusion. Now, going back to what Madhav was asking, you could use what I just said here to answer your question, right? Because again, right, I mean, at the end of the day, you just really have to put yourself into the context of what the alternative is saying here to understand, right? Here, right, the alternative, you only go with the alternative if the true population mean is bigger than your proposed value, mu naught, right? So in other words, X bar here, right, being the stand-in for your mu naught, right? I mean, for example, let's just be concrete. Let's say your mu naught is going to be 2, right? Let's suppose that your S over root n is equal to 1 for some reason, so we don't have to divide it. Let's say your X bar is equal to 4, okay? Then when you calculate your p-value, you would calculate the probability that Tn minus 1 is bigger than 2, right? But so basically, roughly speaking, right, in some way, you're calculating the probability that you observe more extreme value than 4. In other words, what I'm saying is like the direction of bigger is the only direction you care for in this case. You do not want to care for the less than. Why? Because you the population mean, right, is not meant to be small. You understand? Like if X bar is 4, then you only care for more extreme value than 4, right? Because if X bar is small, that does not kind of correspond to the true mean being less than 2. You understand? So again, right, think of X bar as really the stand-in for mu, right? That's the estimator for mu. So why do you care for X bar being small in this alternative hypothesis? Because you are really looking for X bar being the true mean being big. Is that okay? I mean, that's the most intuitive I can try to explain without going to all the details on, the calculation should work out that way. But yeah, I mean, like, you should really contemplate for yourself why this goes like this and this goes like this. Absolutely. In the other one-sided test, right, in 3, the null mu equals to mu naught, the alternative mu less than mu naught, right? So what is our rejection region? We would reject if the test stat, yeah, you tell me, what is the rejection region here and what's the p-value here? Wrong, right? Wrong in the sense that you missed the minus sign. Oh, sorry, alpha. Do you see? There's a minus sign there. Why? Because supposedly this minus this should be a negative number. Okay. So there's a minus sign here, first of all, right? You understand? Because again, if X bar is not less than mu naught, then actually this should not be likely to be true. So again, it's obvious, but it's that, right? There's a minus sign. So what's the p-value, right? The p-value is the probability that T n minus 1 less than this. So this is fine, actually. Oops, let me write it down here. Yeah, without any modification. Like that only, right? Why? Again, right, I guess the picture is still the same. And if you have this picture in mind, that might help. So this is the T curve, right? So here is minus Tn minus 1 alpha, right? In the rejection region, you try to search for T in this area, right? If T is in the, sorry, the test stat, right? If your test stat in this area, then you don't reject, right? So it's, on the other hand, right, in terms of p-value, this is supposed to be this value, and this is your p. You see, the point is it kind of points to the same region anyway, but what this guy is different. There are different roles, right? By the way, right, this value is supposed to be negative in itself. Why? Because if that's not true, right, then your null is not, your alternative is not likely to be true to begin with. Do you understand? Yeah. But I don't know if I'm making too much of a big deal out of this, right? The negative is baked into this, while the negative must stand out in the T thing, right? So let me ask you this, right? In this test stat, in 3, is it possible for x bar minus mu naught divided by s over root n to be positive? How can s over root n be negative? What is s? So yeah, okay. So is it possible for x bar minus, is it possible for the test stat in case 3 to be negative? It's possible. It's possible. Okay, so again, maybe this is the confusing thing about stat, but you gotta distinguish this. All right, why? Because you don't control the sample. The sample does whatever it does, right? You control the hypothesis. You control how you choose to reject or accept. You don't control how the sample behaves. So, I mean, I don't know, right? The sample can be quite wacky, or you can pose the wrong hypothesis so that this is true, right? So do not get into the, fixation that somehow this has to point in the right direction. That's not that. That's the most reasonable direction that they can go. But if this is positive, that's fine. What if this is possible? What if this is positive? Then what do you do here? Who say that mu is bigger than mu not, right? Exactly, you just don't reject. You see that, right? Exactly, that's why I want you to get into Madaf, and Alice got the right answer, right? This is not, right, facts in life. These are your hypotheses, right? It can be true like this, or it can be true like this, who knows? You just have to set up the most reasonable things for you to reject or accept. So here, of course, if x bar is bigger than mu naught, then how can this be true? So you just, accept the no, that's it. And you see that, right? Of course, if this is true, then your p-value is guaranteed to be bigger than 0.5. You see that? If this is bigger than 0, then p-value is guaranteed to be bigger than 0.5. And if you reject when p is quite small, right? Then of course, here you accept. All right. Now, I don't want to spend too much time on this. The reason is not because I don't want to explain it to you. The reason is you must spend time with this kind of stuff and then contemplate and then, you know, kind of see the meaning of it. All right. But I hope I have pointed out all the things that are usually, right, trapping for thoughts in these kind of things, that people tend to take this as, you know, gospel, like this must be true or false. No, this is a hypothesis. All right. You get to pose whatever you want. You only can answer you can only go with the decision as the evidence points to your eyes. That's it. That's all you can do. All right. So the sample can do whatever it wants. Yeah. All right. So, but again, right? Think of this as investigation. Okay. These are not like fixed facts. Of course, when we really simulate data, then we can simulate one of the idea. But all right. But yeah, think about it a little bit. All right. You gotta play with it to get intuition. Any other question before we do the I show you the code? Right, the code will be real quick. Gonna be easy too, but hopefully gonna bring the p-value idea right to you if you haven't seen it. Let's see here. Right, so I hope you see this, right? So here, I was doing a sample of size 9, right? Is normal sample. I will do this hypothesis test, all right, which is the you know, two-sided, right? And testing, right? So mu 0, mu naught is 0, 0 here, right? And I run the sample, right? And you see that the true mean here, I guess I didn't show to you, but I guess the true mean is 2, right? Which makes the null hypothesis true, all right? And so I run the sample, right? I get the test that. I get the you know, this is the percentile, and I compute the p-value. Okay. So I want you to pay attention to this. We're going to run it a couple of times. But first of all, notice that the sample will change, right, every time I run it. Of course, it's a random sample. Second thing is, notice, do I reject or accept? Okay. For example, here, right, do I reject or accept? I reject, right, because, you know, the test stat is bigger than the percentile, right? Remember, you reject when the absolute value here is bigger than this, right? And what about p-value? I will reject if the p-value is less than alpha, right? So here, the decision between this test stat and the p-value are the same. Okay, so let's run again. So, right, see, test stat is bigger than this, p-value is this, right? One more time. Oh, yeah, this is slightly, right, bigger, and this is true, right? But notice that, of course, because the alternative hypothesis is true, right? You tend to reject, right? This test performs what it's supposed to, right? It does, right? It does pick out the right one. Okay, so let's change the true mean to be 0 and see what happens. If the true mean is 0, you see the test stat is very small, the p-value is very high, right? And you do not reject here, right? The true mean, right, is 0. Okay, and I think this is exactly what Madhav was asking, right? You see, you do not get to control what the sample looks like. You don't get to control what mu is, right? So mu was 2, then mu is 0 now. I can make mu equals to 1, for example, or mu equals to -5 for whatever reason, right? But if mu is equal to -5, right? Notice that my test stat is also very big, but in the negative direction. So the alternative, right, is still true. I can still detect, you see, that the absolute value of this is still bigger than this, right? and the p-value is very small. So this is a two-sided test, right? Where I show you mu equals to 2, mu equals to 0, and mu being negative, right? What you want to pay attention to, and notice, right, the sample here is mostly negative. Why? Because the true mean is -5 and sigma is 1. So they're mostly negative numbers, right? And again, the message is you should try to see that the rejection, right, decision based on the test stat is the same as the rejection region based on the p-value. So when you go to one-sided test, right, when you go to one-sided test, so here, oh, now that you're curious, it's very easy. And this is why I think if you ever take up, I think in a class that stat class that use R and stuff like that, in Python, right? What you would do is you would use this command right here. NPy is just a NumPy, library. You go this. That would generate n normal values for you with mean mu and variance sigma. Standard deviation sigma. So yeah, this is magical. They just do it for you right here. Of course, the question of how do you do this exactly, mathematically is a question that you can learn in a Monte Carlo simulation class, which is very interesting by itself too. But yeah, I mean, the answer is very simple. Just pick up a coding, program. They all have their own package for you to do this right away. All right, so in the one-sided test, right? In one-sided test, right? So here, the true mean is -1. So again, right, this is true. Let's see, right? You see, for example, here, right, the test stat is not less than this minus t value. So I do not reject, right? I do not reject. Even though you see, the true mean is true. The alternative is true, right? The alternative is true, right? But I do not reject. And this, I made an error here, right? I made a type 2 error here. But notice the p-value is also slightly bigger than alpha. So I also do not reject using the p-value. So it's consistent, right? The fact that I make an error is fine, right? I mean, I designed the test doesn't mean it's error-free, right? It cannot be. They're always error due to randomness, right? Let's run again. This time I do reject, right? I do reject because the test stat you see is strictly less than this, and the p-value is smaller, 0.01. Okay. Now again, right? Let's show you what if the true mean, right, is 1. Wait. Yeah. Anyway, I guess you see this is kind of weird, right? If the true mean is 1, then the alternative is actually false. But this is exactly where, I guess, in the test of significance, right? They say that you either reject the null or you hold your evidence, right? I mean, like you hold your judgment. So here, right, clearly, you do not have enough evidence to reject the null because, right, you see that the test stat is not less than the minus t value. The p value is big, but right, I mean, I guess mu equals to 1 doesn't mean equal to 0. So that kind of demonstrates, right? So here the conclusion is you do not reject the null, the alternative. You do not reject the null, right? But you don't quite adopt the alternative either. Anyway, right, I just want to show you that the test stat direction, the p-value direction are consistent, right? And I guess here it also kind of shows why you do not want to say you adopt the null exactly if you don't reject, if you don't go with the alternative. Any question? All right, so again, right, I mean, you can play with this if you want. I think it will help you build some of the intuition. Again, all these things, you got to do them at some point to get a feeling. So All right, so now my goal is to go very quickly over test 1, 2, 3 for different categories. So so what we did, right? We finished with test for the mean. Okay. So now we do test for sigma, right? So we have x1 up to xn, IID, normal mu sigma square, right? Both unknown. So I would just write down test of type 1, right? And type 2, type 3, we can kind of just understand. So questions, right, for you. What's our test stat? What's our rejection region? And what's our p-value? Right? And I guess exactly this is the thing you want to know, right? Posing a hypothesis. And by the way, we won't deviate too much on the population. There will be some approximate tests, but I don't care for that, when central limit theorem kicks in, right? But let's just focus on the exact case first. So given this, what's the test stat? What's the rejection region? What's the p-value? If you can answer this guys very quickly, then you would know what this is all about. Anyone? What's the test stat? Okay, not bad. So S square, I would agree. No. Okay, you can do that. Not bad. That depends on how you define the rejection region. How would you define the rejection region? You see, now you have to think, right? I would propose my test stat like this. Right. Right, both of you are right, but you see that it's most natural for me to pose my test stat like this. Right? Then what's my rejection region? So let's call this T of X, right? What's my rejection region? Rejection region is T of X is bigger than or equal to chi-square n minus 1 alpha over 2, or do you agree? Why the or? Because it's a two-sided. What about the p-value? So actually, let me write down, right? For if you have the alternative as sigma bigger than sigma 0, okay, then you reject when T of X is bigger than or equal to chi-square n minus 1 alpha over 2. Your p-value will be probability of chi-square n minus 1 bigger than or equal to T of X. If the alternative is sigma less than sigma 0, then you reject when T of X is less than or equal to chi-square n minus 1, 1 minus alpha over, sorry, not alpha over 2, just alpha. Alpha. And the p-value would be the probability that chi-square n minus 1 is less than or equal to t of x. Are we okay with this? What about the p-value for the two-sided case? I'll let you contemplate that a little bit, okay? But notice that the difficulty here is exactly because the chi-square is not symmetric. So if you go with something like p of chi-square n minus 1 is bigger than or equal to t of x, or chi-square n minus 1 is less than or equal to what? Right? Because basically, you know, you cannot flip the tx around to get to a minus value, right? In the chi-square distribution. So the picture is like this. This is a chi-square, right? It's from 0 to infinity. So this is chi-square n minus 1, 1 minus alpha, let's say. So this is chi-square n minus 1 alpha, right? So in the two-sided test, you would reject if your test stat is here or your test stat is here, right? On the other hand, if your test stat is here, what's your p-value? You cannot just say that your p-value is this much, because then you would do the one-sided test, right? You would want your p-value to be something over here too, but what is it? Do you understand? So, right, because you would reject if your t of x here, right? In this one, the intuition is that you would reject if t of x is very large or very small, right? Very large meaning is, you know, large, that's fine. But very small here means close to 0, not very negative, all right? This is the difference between this and the test for the mean. The test for the mean, you're fine, because, you know, very large is on this side, very small is on this side, right? Negative. So the symmetry helps. So you just have to flip the sign. Here, very large is here, but very small is over here. How do you handle the two cases together? All right. So I'll leave that for you to contemplate, and I'll put that on a quiz question. There's no one single answer for this, but think about it, because, you know, again, right? If you use software all the time, this p-value is just gonna produce for you automatically. But you want to peek under the hood a little bit and think of, okay, how are these values produced? Because otherwise, right, you probably won't have a good control of what's going on. Any question on this? On how I come up with a test stat, with the rejection region, etc. Except for this case, of course, the p-value here, which we did not answer exactly. Again, right, I did go a little quickly because I think all of these. Oh, you mean here? You mean here? No, right? Because I mean, if we understand that sigma is always positive, right, which we do because that's a stand-in for standard deviation, then these are equivalent, right? Yeah, the square function. I mean, yeah, something like that. So you can do this or you can do this, I think. Yeah, right. Because again, if sigma is non-zero, then we may have an issue like this. But sorry, if sigma is not always positive, right, then we may have an issue. But right, no one would say sigma is negative because it's a standard for standard deviation. So square or not, it says the same thing. Any other question? Okay, so now we get to a test for two. So test for two different tests for two population means, right? Mu1, mu2. So something like this, right? You have x1 up to x n1, right? Let's say with normal with mean mu x, variance sigma square, y1. So I just switch to x and y just to make notation easy. y1, y n2, right? Normal with mean mu y, variance sigma square. Right, you see what I'm doing there. So all these are unknowns, but I make a very special assumption that the sigma square are the same, right? Let's say that my null is mu x is equal to mu y. My alternative is mu x is not equal to mu y, right? And we have all the other variations less than or equal to, bigger and equal, less than and bigger than. All right, so let's now test that. What's our rejection region? What's our p-value? Well, this is really a test of your memory. Do you remember what we did for the confidence interval? Absolutely. Oh, no. Actually, if they are known, then you can do this actually. If the sigmas are known, you can specialize to the case when they both are different. Because they're unknown, that's why we only do, they're the same. With obvious reason. Go go back to the confidence interval and see the discussion there. But was a test that? Well, no, this is not pair. Sorry, this is not pair sample, Alice, because I guess maybe they're independent, I guess. No, it's fine. You're quite good actually. I mean, like I forgot I mentioned that even, but here because I do n1 n2, right? I don't assume they're equal. So pairs, I'm not really having pair sample in my mind. But your approach is fine, right? Except that here I have independent samples. So well, what I have in mind is something like this, right? You have x bar minus y bar divided by SP square root of 1 over n1 plus, wait, hold on. Yeah, 1 over n1 plus 1 over n2. Very good, Madaf. Excellent. Except you should have minus y bar, right? And then do you see what happens with your mu x and mu y? Oh, and by the way, right? I guess you have both pluses there. They should both be minuses. Do you agree? Fine. No, it's good. It's almost there, right? But notice what happens with your mu x minus mu y. Notice, right? Do we know what mu x and mu y? So Your test stat should not have anything that's unknown, right? I mean, actually, you propose something very good, very educational, right? Your test stat should not have anything unknown. So what happens to your mu x and mu y? You are absolutely right. This is actually should be the one. But what happens to this term? This term vanish under a null, right? This term vanished under a null. And that's exactly why I say that this is a simple hypothesis, in quote, right? This is a simple hypothesis because under this hypothesis, that term vanished. And I can decide exactly the distribution of this, right? Which is T n1 plus n2 minus 2 distribution. Are we okay? And this is the pool variance, right? This is the pool variance estimate. Are we okay? Question. When do we reject? We reject if the two-sided, right? Then you reject when? So let's call it T of xy, right? We reject when T of xy absolute value is bigger than T n1 plus n2 minus 2 alpha over 2. Right? If it's one-sided upper, for example, oh, let's do this. Who knows what's upper, what's lower, right? What about this? If mu y is bigger than mu x, then what is our rejection region? If mu y is bigger than mu x is our alternative, what's our rejection region? If it's true that mu y is bigger than mu x, less than minus t, Christine, right? Less than minus t, right? Because this will tend to be negative, right? So you're quite there, except that it should be minus. No, test that less than t, less than minus t. So t xy less than minus right? Because again, if you call this your test stat, then x bar minus y bar will tend to be negative if your alternative is true. Sorry, no alpha here. What? No, if you multiply minus 1, don't you switch the sign? You can do that too, yeah, sure. No, it's fine. It's very easy to get confused here with direction. I know that. So right, so yeah, getting the direction right. And again, how do you get the direction right? By understanding what this means, right? I keep emphasizing you gotta read your stat. It's not like you just plug in the formula, right? You know this stand in this stand for this stand for this. That's why when this happens, this tends to be negative, etc. Then you won't make a mistake. Okay. So p-value would then be, I mean, let's say for two-sided, right? Then P would be probability that the T distribution is bigger than the absolute value of your test stat, right? And let's just make you more confused. Suppose that the Alternative is mu x is bigger than mu y. What's my p-value? So here's my test stat, right? If mu x is bigger than mu y, what's my p-value? Oh, you know what? I think I kept making mistake. I'm really terrible. There's a 2 here. There's a 2 here for the p-value for the two-sided. I think I got that mistake. You know, lead into in my code as well. There's a 2 here because it's two-sided. Sorry. So in the two-sided, somewhere. Not in this, because I did not write what this is. But in here, right? What's my p-value? Right here. There's a 2 here. There's a 2 here. All right, because of the two-sided. All right. I hope that's it. Yep. So for the two-sided, right? There's a 2 times probability. The reason is basically, you know, either, right, this is extremely large positive or extremely large large negative, but or means add, and these two probability are the same. That's why you get a 2. Yeah, I forgot that. Anyway, right, if mu x is bigger than mu y, what's your p-value? Well, it should be the probability of t and 1 plus n2 minus 2 is just bigger than tx1. Is that okay? Because if mu x is bigger than mu y, this tends to be positive. Question? What was the p of y less than x? So if mu, wait, hold on. You mean mu y is bigger than mu x, you mean? Oh yeah, bigger. Yeah, of course, that's what you said. Then this tends to be negative, right? So it will be probability that t n1 plus n2 minus 2 is less than, like that. But you know, like I know that you're trying to type, so you try to type short. But there are 2 things that you want to pay attention to, right? There's a t for the t distribution, and there's the big T for our test stat, right? You want to know which one is less than which. Because obviously, if you swap these 2, then you don't mean the same probability, right? Is this okay? Question? Again, right? If you want a picture in mind, this is a t distribution, right? So your test stat should be quite big or quite small for you to reject. For example, so it can be either here or here, right? For you to say that mu x is sufficiently different from mu y. And so that's why when you compute the p-value, you add both. Like this, right? This is two-sided. But when you have the one-sided, right? Suppose that mu x is bigger than mu y, then that's only true if, right, this guy is sufficiently large. Okay, that means that the only chance that happens is your t value, your test stat is ending up here. Therefore, this is only your p-value. Similarly, if mu y is bigger than mu x, then your test stat is sufficiently small. That's the only chance when that happens. So this is your T, your test stat, and you reject when this is small. So that's the picture. Again, right? It is all because of how you construct this test stat. All right. So question for you. What if I change my hypothesis like this? What if I don't want to compare the mean exactly, right? I mean, that sounds restrictive, right? So in other words, same setup, except that I don't want to test that the two population of my means are exactly equal. For example, if I compare the height, right, of boys and girls, I mean, boys tend to be, right, taller than girls. Why would I say they're equal? I would say maybe I want to test them the fact that the boy's height is 1 inch, whatever, you know, on average above girl's height, right? Then I would translate my hypothesis like this. Okay, same setup. How would I construct my test stat? You know, my rejection region, p-value, etc. So one thing for you to note, right, is that this hypothesis test, even though it's on two, right, on this, is really a test for the difference, right? It's really the test for the difference of the mean. In other words, you can translate like this. And I think that's actually the true point of view. Even though, right, it sounds like a test on two samples, which it is, right? The parameter is actually a one parameter, is on the difference of the means. So therefore, you see, that's why x bar minus y bar is the guy, because, right, it is the estimator for mu x minus mu y. So therefore, right, you throw in a delta, that doesn't change anything. The test stat will be x bar minus y bar, whoops, minus delta divided by SP square root of 1 over n1 plus 1 over n2. That's it. The only difference is, right, now you do x bar minus y bar, but you also subtract the delta. So, right, I mean, this exactly is like the null, mu x minus mu y is equal to delta. The alternative, mu x minus mu y, is not equal to delta. So actually, you see that this is very much like the one sample mean test. It's exactly like a one sample mean test, except when you use x bar, here you use x bar minus y bar. This is exactly your mu naught right there. Okay. And rejection region is the same, actually. Rejection region is the same as the above. The reason is, right, once you construct the right test stat, it has the same distribution, which is the, you know, this guy is t n1 plus n2 minus 2 under the norm, right? Because under a norm, this delta vanish. And so you get exactly to the t distribution. Okay. So the fact that you add an artificial delta in there doesn't change anything. Any question? Okay, so we have one more test to talk about, the test of, the two, comparing the two variances, and then we'll be done with, chapter 13. And then next week, we're gonna spend a little bit of time on, regression and all that good stuff. All right, so thanks for attending, guys. If you have questions, I'll answer. Yeah, if not, then I'll see you next week. Thank you.
Hi, Professor. I had a quick question on the quiz. For the last part, we just plug in the K values that we got in part B, right? And then solve for beta.
Yeah, absolutely. And you should get that, the region using, S prime square has lower beta than the region using S square. Yeah.
Okay, and that's it, right? Okay, yeah.
Mm-hmm.
Okay, cool. Okay, thank you.
Sure. You too.